Welcome to the second episode of PHS Physics SOS. This week I will be going over the homework for Chapter 2, Part 2. But first I'd like to encourage everyone to try the homework first before just watching these videos. It really doesn't help you just to watch someone do it. It will help you a lot more if you try it on your own and then come back and look for the problems you need help with. The times in the video that each problem start at will be linked in the description, so if you only need one problem and it's in the middle of the problem set, just find it in the description, skip to that part of the video. Anyway, on to the homework. The first question is question 18, and it reads, what is the acceleration for a turtle moving with a constant velocity of 0.25 meters per second to the right? Now, this question is more of just a vocabulary question. It's just making sure you know what constant velocity means. Now, when you have a constant velocity, it's always going to mean that the acceleration is zero, because if your velocity is constant, that means it's not changing. And since acceleration is change in velocity, and if your velocity is not changing, that means your acceleration is zero. The next question, question 19, says sketch the velocity time graphs for the following motions. A city bus moving with a constant velocity. So we draw our axes. We have time on the x-axis and velocity on the y-axis. So moving at a constant velocity. So constant velocity is just going to be a straight line at some arbitrary constant c. And you don't have to write that. That's just showing that it's at one point. It's not moving. It's at constant, hence constant velocity. Part B says a wheelbarrow speeding up at a uniform rate, moving in the positive direction. Again, label our axes. So let's dissect this. A wheelbarrow moving at a uniform rate. A wheelbarrow speeding up at a uniform rate, moving in the positive direction. So speeding up at a uniform rate means constant acceleration. And remember, acceleration is the change in velocity over change in time. So just like velocity is the change in position over the change in time, so if we have a position versus time graph, velocity is going to be the slope of this graph. Slope equals velocity. If we have a velocity versus time graph, acceleration is going to be the slope of this graph. So again, let's go over that real quick again. Like, as we've already learned, velocity is the slope of a position, x, versus time graph. But acceleration is the slope of a velocity versus time graph. So, back to our problem. A wheelbarrow moving at a uniform, a wheelbarrow speeding up at a uniform rate, moving in the positive direction. So, speeding up at a uniform rate, as I said, means constant acceleration. So if it has a constant acceleration, that means the slope of the velocity is going to be constant. So it's just going to look like this. Also, it says moving in the positive direction. That means the velocity has to be positive for it to be moving in the positive direction, and that just means greater than 0, and this is positive. Had it said speeding up at a uniform rate and moving in the negative direction, well, we'll get to that later. It's one of these parts. In fact, it's part C. Again, draw our axes. So part C says a tiger speeding up at a uniform rate and moving in the negative direction. So speeding up means, now you have to be careful, because speed is the absolute value of velocity. So if the absolute value of your velocity is increasing, that means you're speeding up, but that doesn't mean your velocity is increasing. Now let me explain what I mean. So the answer to part C is going to be this, because the speed is the absolute value of the velocity, while this is negative something meters per second. Let's just call it negative 5 meters per second. Wow, that didn't make any sense. Negative 5 meters per second. If we call this negative 5 meters per second, and then down here it's at negative 7, God, I can't do this today. If it's at negative 7 meters per second, that means the velocity has decreased. So it's decelerating, because deceleration is a negative change in velocity. However, it says the tiger is speeding up, so you'd be inclined to think that this is wrong. However, since speed is the absolute value of velocity, and if our velocity is negative 5 and negative 7, the speed would be 5 and 7 meters per second, respectively. So while the velocity is decreasing in this particular instance, the speed is actually increasing. Part D asks, it says, an iguana slowing down at a uniform rate moving in the positive direction. So it's moving in the positive direction, which means we're up here somewhere, because for it to be moving in the positive direction, the velocity has to be positive, because if we draw a little x versus t graph, for it to be moving this way in the positive direction, the slope has to be positive, so the velocity has to be positive, so the velocity has to be above 0. So an iguana slowing down at a uniform rate, moving in the positive direction. So as we said, it has to be above the x-axis, and slowing down means the velocity is decreasing. So our velocity graph is actually going to look like this. So the velocity itself is decreasing, but it's still positive. So your position is still increasing. It's just increasing at a slower rate because the velocity is decreasing. And this isn't the graph. This isn't the position graph of this velocity. This was just an example. Ignore this. And finally, part E says a camel slowing down at a uniform rate, moving in the negative direction. So moving in the, actually let me redraw this. Let's see, can you see this? Yes, you can. So the camel's moving in the negative direction, meaning that our velocity has to be below 0, but it's slowing down. So that means its speed is decreasing. And like we talked about over here with the absolute values and such, that means the graph is actually going to look like this. Because it's moving in the negative direction, because the velocity on this graph so far is always negative. But it's slowing down because this speed here is less than this speed here. Because as we said over here, speed is absolute value of velocity, so if this was like negative 6 and this was negative 1, the speed would be 1 or 6. So the speed has decreased from here to here, but the velocity is actually increased, but that's not what the problem's asking. And again, at a uniform rate means constant slope, so no squiggles like this or like this, none of that, just a straight line. Question 20 is another stupid question, but I'll get to that in a minute. Question 20 says, the strobe photographs in figure 2-22 show a disk moving from the left to the right under different conditions, and those are these pictures down here. The time interval between the images is constant. Assuming that the direction to the right is positive, identify the following types of motion in each photograph. So what they mean by assuming the time interval between each image is constant, that means the distance between each one of these points, each one of these images of the disk, was taken the same amount of time apart. So between the time the disk was here and here was, say, half a second, and then here and here was half a second, and here was half a second, but it covered more distance, so we know there's going to be something different about its motion. We'll get to that in a minute, and so on and so forth. So Part A wants which parts have positive acceleration out of these three. So positive acceleration means the velocity is increasing, and we can see increasing velocity by increasing distance between images of the disk, because as the problem said, hang on, let me move this up. Hopefully you can see that a little better. Since velocity is defined as change in distance over change in time, and if the change in time between each one of these images is constant, um, but the change in difference is distant, is bigger, then we can assume that the velocity between those two points increased from a previous point where the distance is smaller. In other words, it's accelerated. So, so what we're looking for is changes in distance between disks, as almost like velocity vectors. So this one down here, the first change in distance between the disks is very small, so it's very low velocity. The next one's bigger, so the velocity's higher. The next one's even bigger, so the velocity's greater. I keep using different words. Greater magnitude. And the last one's even bigger, so the velocity has an even greater magnitude. Meaning that the velocity has been increasing the whole time over this interval for the last one, meaning the acceleration is positive, which is a. Now this one, the distance between each one of these disk images is the same each time, meaning that the velocity is constant, which is c. Velocity is constant. Now, here's where the stupidity comes in this problem. The way it's worded, it doesn't explain this very well, but this image up here actually satisfies two of these, and it wants you to know that one of them is for one half, and one of them is for the other half, and that's really stupid, but go with it. So the first half of this image is kind of like this one down here, where the distance between each disk is increasing. A small distance, a little bigger, bigger. So it's accelerating because the velocity is increasing. But the second half of the image, you've got big, small, and then we can only assume that it gets smaller. So the acceleration is negative. So the answer actually says that the left half, the acceleration is positive, and the right half, the acceleration is negative, and somehow you're supposed to know that for this problem you're not expected to match each one, you're just supposed to assign one to the other, and it's a really stupid problem. Don't worry about it. Question 21 says, if a car is traveling eastward, can its acceleration be westward? Explain and use examples. So we're going to draw our compass first, and this is 21. 21, not 2 exclamation mark. North, east, south, west. So, since we're only worried about east and west, we're going to cross out north and south as not to confuse ourselves. And we're going to define, since it's moving east, we'll call east positive and west negative. Because we need, you'll see in a second, we need to define our directions. Call that a car, pretend it's a window, get over it, I can't draw. Whatever. So let's say the car initially has a velocity of 10 meters per second east, which is positive. And then later, let's say 1 second later, it has a velocity of 5 meters per second east, which is also positive. But in that time, the car is traveling eastward, so it's traveling in the positive direction, but its acceleration is negative because the velocity decreased. So the acceleration is in the westward direction. So this is a velocity vector. This is a velocity vector. We'll call this v0. We'll call this v1, and we'll call a0. This is going to be a0. This is negative 5 meters per second squared. Because between v0 and v1, which was we defined as 1 second, the velocity decreased by 5, and since acceleration is change in velocity, that means acceleration was negative 5. And since west is east, west is not east, since east is positive and west is negative, that means our acceleration is negative and in the westward direction. So the answer to the question is yes. The next question, question 24, reads, a snowmobile has an initial velocity of positive 3 meters per second. So v0, or v sub 0, is initial velocity. You can also write it as v sub I, or whatever you want, or v0, a million ways to write it. And you don't necessarily need to be able to use all of them, but you should recognize that they all mean initial velocity. So it says it has an initial velocity of positive 3.0 meters per second. Part A says if it accelerates at the rate of positive, so acceleration equals positive 0.50 meters per second squared. For 7 seconds, what is the final velocity? So we're going to use the equation v final equals v initial plus acceleration times time. So we want to find v final, so that's what we're looking for. Our v initial is given up here. It's 3.0 meters per second. Our acceleration is 0.50, and our time is 7 seconds. So we just multiply it out, add it together. There you have our answer. Just plug and chug. It just this problem is just testing that you know this formula. V final equals V initial plus acceleration times time. And if you don't believe this works, and if you don't understand why this works, try working out the units. Velocity is in meters per second. Velocity is in meters per second. Acceleration is in meters per second squared. Multiply by time, which is on the top of the fraction. Make sure you don't put it on the bottom, so over 1. And time is in seconds. So seconds, sorry. I got unit variable, sorry. Seconds. So when you multiply that out, you get meters per second equals meters per second plus, and these cancel. Well, that one cancels with one of these, plus meters per second, and then you get meters per second equals meters per second. So unit-wise, it works, and that's a kind of a good way to make sure that you have the right equation. So part B asks, if it accelerates at a rate of negative 0.6 meters per second, so A equals negative 0.60 meters per second squared. I think I said meters per second a second ago. Should be meters per second squared. If it accelerates for a rate of negative 0.60 meters per second squared, how long will it take to reach a complete stop? So again, this is just testing the use of the same equation. So it wants to know how long it's going to take to reach a complete stop. And this is another little vocab thing. You have to be able to translate words into numbers. So complete stop means final velocity equals 0. So we're going to use this equation again. So 0 equals the initial velocity, which is given up here. Oh, and another thing that this problem doesn't really explain is part B is not after part A. Part B is like starting over with the same initial velocity, which could very easily confuse people. And it confused me. So where was I? So 3 plus our acceleration, which is given right here. Negative 0.60 times time, which is what it's asking for. So again, this is just testing the knowledge of the same equation. It's just giving you different variables, and it wants an answer. So negative 3 equals, and it's just plug and chug from here. Just do the algebra real quick. So then negative 3 over negative 0.60 equals time equals 5 seconds. Question 25 says, a car is moving westward along a straight level road. A car moving westward along a straight level road increases its velocity uniformly from positive 16 meters per second to positive 32 meters per second in 10 seconds. So, again, this is the whole translating words into numbers. So, increases its velocity uniformly from 16 meters per second. Okay, and this is number 25. So from 16 meters per second, that means our initial velocity is going to be 16 meters per second to positive 32 meters per second. So for now, we're going to assume that's our final velocity in 10 seconds. Now part A asks, what is the car's acceleration? So the way we want to calculate this is the same equation we've been using. V final equals V initial plus A times time. So 32 equals 16 plus 10a. So 16 equals 10a, 1.6 equals acceleration. And that's in meters per second squared. Part B asks, where's my problem? Part B asks, what is its average velocity? So the average velocity is just going to be 1/2 of the initial velocity plus the final velocity, which is going to be, because our initial and final velocities are given in the problem, so this is going to be 1632, 48 half is going to be 24 meters per second. And part C asks, how far did it move while accelerating? And this is going to take a new equation. Well, actually, no, never mind. There's two ways you can do this, and I'm going to explain both ways. I lied. There's 3 ways you can do this. I'm going to explain all 3 ways. First way, easiest way, you take your average velocity times your time, and that will give you your total distance traveled. Or delta x, whatever you want to call it. So we take 24 times 10. That gives you 240 meters. Second way to do it, actually never mind, you don't need to know the other 2 ways because we'll get to one of them, and the third one I don't think you even need to know. And if you do, it'll be explained later. Question 27 reads, a plane starting at rest at the south end of a runway undergoes a constant acceleration of 1.5 meters per second squared for a distance of 1,600 meters before takeoff. Wow, that's a lot of information. Let's draw a picture. So this is 27. And we'll draw, let's see, what end is south end of a runway. My pen's dying, isn't it? I am going to get a new pen. I'll be right back. Okay, we're using blue now. I hope that doesn't mess with your mind too much. So here is our runway. South, north. So it starts at the south end of a runway. Here's our plane. It's a plane, get over it. And an acceleration of, we'll call this our acceleration vector, and it's 1.6 meters per second squared. And for a distance of 1,600 meters. So this is 1,600 meters. Part A asks, what is the plane's velocity at takeoff? So we have an acceleration and a distance, and now we're going to learn a new equation. The equation is, hang on, my screen just decided to go black. Okay, so the equation is v final squared equals v initial squared plus 2a times delta x. And just to go over all these variables real quick, this is your final velocity. This is your initial velocity. This is twice your acceleration, and this is your change in distance, or your displacement, your delta x. So, part A wants the plane's velocity at takeoff, which is going to be our final velocity. So v final squared equals v initial squared, and it tells us in the problem that the plane starts at rest. Again, this is interpreting words into numbers, so that means the initial velocity is 0. Plus twice the acceleration times the change in displacement. Now we multiply all these out, and we get 3.2 times 1,600, which equals 5120 meters squared per second squared. And if you can see, when we take the square root of this to find the final velocity, we're going to get meters per second, so we know we did it right. So take the square root of both sides, get v final equals 72 meters per second. So part B asks, what is the time required for takeoff? Oh, and this equation, by the way, is called the timeout equation. Because there's no time variable in it, but it has all the other important stuff. It has final velocity, initial velocity, acceleration, and change of position, but no time. So it's easy for solving problems when there's no time. There's other ways to do that problem, but usually you're just going to end up deriving this same equation anyway, so it's easier to just memorize it, because you're going to use it a lot. So what is the time required for takeoff? So we're going to use V final equals V initial plus acceleration times time. This is the one we've been using in our other problems. And this is A, this is B. So V final is 72 equals V initial plus 1.6 times time. And if we divide these out, we get 72 equals 1.6 times time. And then you divide it out, you get 44.7 seconds equals time. And there's your answer. And this is the answer to part A. Question 28 reads, a bus slows down uniformly from 75 kilometers per hour, or 21 meters per second, to 0 kilometers per hour in 220 meters. How long does it take to stop? So again, this is going to be using the same equation we just talked about, the timeout equation, V final squared equals V initial squared plus 2a times delta x. And the reason for that is because to solve this problem, the first thing we need to find is the acceleration to be able to find the time. So V final squared, it gives us V final in the problem. It's 0 kilometers per hour, which is the same as 0 meters per second. And it gives us the initial velocity, which is 21 meters per second. Plus 2a, which is what we're looking for, times delta x, which is 220 meters, also given in the problem. I should probably write these all down. So the initial equals 21. The final 0, delta x equals 220. Getting lazy with my units. So now to find our acceleration, we want to go negative 21 squared equals 440a, and negative 21 squared is, actually, I should draw that better. The negative's on the outside of the parentheses. So 21 squared is 20 times 22 plus is 441. Don't forget the negative sign, because the negative sign's outside the parentheses, so you don't square the negative. You apply it afterwards. Equals 440a. So we divide those out. We're going to get acceleration is equal to negative 1.0 meters per second squared. So this is a two-part problem. This isn't even the answer to part A. This is just what we need to use to find the answer to part A. So now we're going to use the other equation we keep using, which is V final equals V initial plus AT. And we're looking for time. And we have everything else. But originally we didn't have acceleration. This is the only way we know how to find it. So V final is 0 equals V initial, which is 21, plus acceleration, which is negative 1 times time. So negative 21 equals negative t, and 21 equals t. So t equals 21 seconds. And that's the whole problem. Thought there was another part. Question 30 reads, a car starts from rest and travels for 5 seconds with a uniform acceleration of positive 1.5 meters per second squared. The driver then applies the brakes, causing a uniform acceleration of negative 2.0 meters per second squared. If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period, and how far has it gone from its start? Okay, so let this little word problem gives us a lot of information. The first thing we want to do is write it all down. So the car starts from rest and travels for 5.0 seconds. So at 1.5 meters per second squared. So, and actually we're going to draw a picture. So the first part, it goes for 5 seconds at with an acceleration of 1.5 meters per second squared. And then it goes for 3 seconds at negative 2.0 meters per second squared. And the question is asking for its final velocity. So this is actually very similar to question 13 in some ways, except question 13 gives you velocities and times and asks for average velocity. But this question is giving you accelerations and times and asking for average velocity, but they work the same way. So you're going to just multiply this by this and add it to this times this. So we take 5.0 seconds times 1.5 meters per second squared plus 3.0 times negative 2.0 meters per second squared. And we get 7.5 minus 6 equals 1.5. Did I do that right? I did. 1.5 meters per second is going to equal our final velocity. The next part of this question is borderline obnoxious and intended to trick you, but I'm going to do my best explaining it. And there's a couple ways to do it, but I think the easiest is going to be the timeout equation, except you have to do it twice, and I'll explain what I mean in a minute. So I start with our timeout equation. The final squared equals the initial squared plus twice acceleration delta x. So if we go back to our original problem, we had this car moving for 5 seconds at 1.5 meters per second squared, and then, or with an acceleration of 1.5 meters per second squared, and then at 3 seconds with an acceleration of negative 2.5 meters per second squared. So the final velocity, the first thing we want to calculate is the final velocity at this point, which is just acceleration times time, which is 7.5 meters per second. So what we're doing is we're doing this equation to find the displacement over this period. And that was a failed bracket if I've ever seen one. So our final velocity is 7.5 squared equals our initial velocity, which is 0. And that's, I believe that's given in the problem. Yeah, the car starts from rest, so the initial velocity is 0. Plus twice your acceleration during that period, which is 1.5 meters per second squared, which is going to be 3.0, times your delta x, which is what we're looking for. So 7.5 squared is 56, and we divide that by 3. You get your delta x, which is 19 meters. The next part of the problem is this. We have to do the same thing, the same equation, for the second part of the problem. And I'm just writing it again so you get it in your brain. This is an equation you're going to need to memorize. If you write it before every problem you use it in, and if you watch it being written, it's going to help you memorize it, because you're going to need it, trust me. So the tricky part for this part of the problem is we have to realize that our initial velocity is not 0. Our initial velocity for this time period, another failed bracket, is this velocity. And our final velocity is the velocity we already calculated down here, is 1.5 meters per second squared. plus twice our acceleration times delta x. I guess I should have filled that in right there on acceleration is -2, so we've got 2.25 equals, let's see, 17.5 squared. I just did this. 56.25 plus acceleration, -4 times delta x. So we get -54 equals -4 delta x. And -54 over 4 is, -54 over -4 is 14 equals delta x. So this is our change in position for this part of the problem. This is 14. And for this part of the problem, it's 19. And when you add those together, you get the total change in position. That wasn't a terrible, that was a terrible bracket. That part ruined it. 19 plus 14, 33 meters. And that is your total displacement. This is an annoying problem. The next question is question 32, and it reads, a boy sledding down a hill accelerates at 1.40 meters per second. If he started from rest, in what distance would he reach a speed of 7 meters per second? So this is another problem where they're giving you final velocity, initial velocity at rest, so 0 initial velocity, and acceleration, and they're asking for a distance. So it's got final velocity, initial velocity, acceleration, distance, but no time. What do we need? The timeout equation. V initial squared plus twice acceleration delta x. So V final squared is going to be 49 equals our initial velocity squared plus twice our acceleration times our change in position. So 49 equals 2.8 delta x. So 49 over 2.8 equals delta x equals 17.5 meters. And in case you're wondering, 7 meters per second is really fast. Don't go sledding at 7 meters per second. You're going to hit a tree, and you're going to get hurt. The next question is question 35, and it reads, a plane lands with a velocity of 120 meters per second. Okay, so again, we're looking for words to numbers. So V initial equals 120 meters per second. Lands with a velocity of 120 meters per second and accelerates at a maximum rate of -6.0 meters per second squared. So our acceleration equals -6.0 meters per second squared. And part A asks, from the instant the plane touches the runway, what is the minimum time needed before it can come to rest? So we've got acceleration, velocity, and time. And so we're going to use V final equals V initial plus acceleration times time. So our V final, it means at the end of the runway, here's our runway, here's a plane. Woo, plane. So it's starting here when it hits the runway at 120, and it's ending at rest, which is 0. So our V final is 0, and our V initial is 120, acceleration is -6, and we're looking for time. So -120 equals -6 time, 20 seconds equals time. Part B asks, can the plane land on a naval aircraft carrier where the runway is 0.80 kilometers long? And to figure this out, we need to figure out how far the plane travels in 20 seconds with this initial velocity and this acceleration. So we're going to use another equation, which is, actually there's a couple equations, so let's use the timeout equation, even though, there's a couple ways. Anyway, so this is part A, this is question 35, this is part B. So V final squared equals V initial squared plus 2A delta x. So V final squared is 0. V initial squared is 120. Twice our acceleration is going to be negative 12, and delta x is what we're looking for. So we subtract over 120 squared equals negative 12 delta x, and then kind of run out of room. Let's do. So 120 squared is negative 14,400 equals negative 12 delta x. Divide that by negative 12, and we get 1,200 meters equals delta x. And the question wants to know, can the plane land on a naval aircraft carrier where the runway is 0.80 kilometers long? And 0.80 kilometers equals 800 meters. And since this is greater than 800 meters, it cannot land on that aircraft carrier because the aircraft carrier doesn't have enough space. Thank you for watching this episode of PHS Physics SOS. If you have any questions, leave them either in the YouTube comments below, or if you don't have a YouTube account, leave them on the Facebook page, which I will provide a link to in the description below. And you can post questions on the Facebook group or message me personally. Thank you.